Hi there. Been a while. Well, for me at least. I don't know, for you maybe it was just one click, but it's been many days since I've done one of these. In real life, we've had a midterm, we've released a big project, but, for you, who knows how time passes. So for the next few lectures, we're going to wrap up Java syntax. This will be it for Java stuff. And then after that, we're going to move on to data structures and algorithms, and that will be the entirety of the rest of the course. So these next set of topics, they aren't super exciting. I mean, you might find them fun, but they're not really big ideas so much as the way Java does stuff. So this is now where we're entering the part of the class known as advanced programming, and most of the work for the course now is going to be focused on Project 2. And so some of these ideas that we're going to present in these lectures will be handy to you in Project 2, and you may see them in the future. Now, this is not going to be a comprehensive look at Java syntax. There's actually lots of other stuff out there that we won't cover ever, and that's just because it's not a Java class, right? We've got what we want after this, and we'll move on. So in this lecture, we're going to talk about autoboxing, promotion, immutability, and generics, and in the next lectures, we'll talk about some more stuff. So let's start by talking about generics. Okay. So for the most part, as you've seen in ArrayDeck and linked list deck, using generics is pretty straightforward. All you need to do in order to use a generic class is you need to provide an actual type argument. So if I have, for example, an array list that someone defined that has some type parameter, then we will provide actual type arguments. And here I've put it both in the declaration and in the instantiation, though of course we learned earlier that in Java 8 it's no longer necessary at instantiation to do so, as long as we're declaring a variable at the same time, because Java will infer that. One thing that we did not talk about was why it is that when we want to create an array list of, say, integers, I just mentioned in an earlier video, why it is that we don't do lowercase int. And so the answer is simply that if you try and do lowercase int, you get a compile time error. So for example, if I were to try and compile this at the command line, I would get array list int yada yada, and the error would be required reference found int. Doesn't like it. And so what this is saying is it expects a reference type, any reference type. So what's a reference type? It's anything that's not a primitive type. And so this is a whole neat hierarchy of reference types that go with the primitive types that we've come to know and love, int, double, those sorts of things. And so for each of those primitive types, there's a so-called wrapper type that represents the reference version of the same idea. Okay? And so this right here, we have byte, short, integer, long, float, and double. And it turns out that actually all of these implement an interface known as number. You're not likely to interface with this number class or interface directly, though it can happen. We also have Boolean and characters, which are not numbers, but all of them are objects, of course. Okay? And so it's these reference types that we're going to be looking at and using. Okay? So as we've seen before, we can say new array list integer. And naively, if we did that, then when we wanted to add a number to an array list, we'd have to do something like l.add new integer 5, l.add new integer 6. Because if this thing's expecting integers, I probably should be giving it integers. And likewise, when I get back a value from an array list, well, when I say l.get0, it turns out that I want to put it into an int variable. And so to get that value back, I can use the value of method. That's part of the integer class that I won't show quite yet. Okay. Now, doing something like this would be super annoying. If you had to manually create an integer wrapper around each of your numbers you wanted to put in an array list, that wouldn't be so great. And likewise, it seems annoying to have to unwrap them. And so at the same time that they released generics, when they added it to the language, they also introduced this neat feature, which is autoboxing and its counterpart, auto-unboxing. So in Java, you will always get an implicit conversion between the wrapper type that goes with the primitive type and vice versa when needed. And so for example, if I say l.add 5, then that int, even though it is just a raw primitive 32 bits that represent the number 5, it will get wrapped up automatically. And so this code right here works beautifully, and you didn't even have to know about this in order to use array lists. However, it is nice to know that this exists, because if you naively proceed, you can occasionally take some significant performance hits. So let's get a sense of what's going on here. Whenever you have code that expects a wrapper type, but you give it a primitive, it will automatically box up the number. So here, for example, is a method called blah. It accepts integers, the wrapper class, and then prints them out. However, if we call blah with a lowercase int, then in that case, it gets automatically boxed up when this call happens. It just happens without you doing anything. Likewise, if we have a method that expects a primitive and you instead give it a reference type, then or a wrapper type around that primitive, then it will automatically unbox it for you. Okay. Now a couple little tiny notes. One is if you have an array of ints, you cannot box it into an array of integers and vice versa. If you actually need to make a copy for some reason, which can happen sometimes, then you actually need to make a manual copy. Another is that the process of autoboxing and unboxing actually incurs a measurable performance impact. So the very fact that the ArrayList class takes capital I integers means that the performance won't be quite as good as a version of ArrayList that is hardwired to handle the int primitive type. Another big issue is that wrapper types actually use much more memory than primitive types, and we'll see just how much in a moment. Now I want to mention that wrapper types are not magic. They don't do anything that your classes don't do for the most part. And in fact, we can click right here. Oh, it's me. We can click right here and we can see the code for the integer class. It's long, has lots of stuff in it. I'm not going to go through this in detail, though I will note that it has a private final int. Yes. One of the things it has is on line 840, it has an instance variable, which is called private final int value. And that, you might imagine, try and guess what that is the value that when you create an integer that you wrap, the thing that gets boxed up, gets put in this variable ultimately. And so you can see that happening right here in the constructor. We can also see, for example, the value of method. Where is that? Value of. Okay, so what does value of do? Well, it's actually a little more complicated than you might have guessed. I won't go into why that is. Okay. Now you've actually used the integer class before. In particular, you used the parseInt method. And so the point here is simply to say this integer class is a lot like the ones that you've written in the past. This one happens to be 1600 lines long, and it does integer stuff only, but that's what it's all about. And you can actually see the authors of this class, including Josh Bloch, who wrote some really lovely books. And I encourage you, if you actually end up going forward with Java, to check out his effective Java, which is quite good. Okay, so the only thing that's special about the integer class, capital I integer, that is different from what you can build in Java is autoboxing and unboxing. You cannot change the behavior of Java in a way that will allow you to do something like boxing and autoboxing, but other than that single superpower of integer, it's just like any other class. So the last little thing I want to say about wrapper types is the amount of memory that they take up. So let's assume, just to get a sense of why, let's assume that in Java all of our addresses are 64 bits, that all of our ints are 32 bits, and all Java objects take 64 bits plus their fields. Okay? And let's imagine here we have the method bleep_blorp, which takes no arguments, creates an integer, and then prints it out. So what I want you to do is think about how much total memory is used by this method to store all of its local variables, and I'll reveal it in a moment. Okay. So these annotations, I actually did them live during the live version of this lecture. So they're already here and they give you a substantial hint. This question isn't super interesting, but I just wanted you to give it thought to it. Because whenever you watch someone talk for a long time and something's not exciting, you kind of glaze over. So this is my way to trick you into actually engaging. Not really a big puzzle. So in this case, the total amount of memory that it takes is, well, let's think about it. Bleep_blorp has a variable called x. It is in an integer. So this box right here is, as annotated, 64 bits. It's an address, effectively, or a reference to something. Then here we have an object that was created. And that object has a single field, which is the one we just saw in the source code, that private final int called value. That's 32 bits. We know that's a 32-bit box. And then we said there's other information, 64 bits of it, that goes with every object. And we're not going to say what that is. I mean, it might have to do with garbage collection or who really knows. But it's just something that every object has, right? You can just imagine it's some secret information scrawled on top of every object that you can't access. So if we just add these up, then it's just 160. So not a lot of depth there. So that's wrapper types in the glorious world of boxing and unboxing.